Day 4, we're going to look at exponential functions. And the intro, we're going to start with this picture right here in our packet. It says, this tree diagram shows a potential coronavirus chain of transmission. Each dot represents an infected person. One infected person, the person at the top of the diagram, spreads the coronavirus to the others, who then spread it onto others, and so on. After looking closely at the graph above, answer these 4 questions. The questions are intended to build on one another, so try to do them in order. So the first question is, what do you notice about the tree diagram? After that, what do you wonder? And then the third question, what impact does this have on you and your community? So in class, we'll take some time to discuss your answers to these questions. And then, one more question. What's going on in this graph? Can you write a headline that captures the graph's main idea? So again, we'll share your thoughts, and then we're going to watch this video about the spreadability of COVID. So let me pop it up.
See that? That's you. And you have the measles. And those dots around you, they have zero protection against the virus. Science tells us eventually you will infect upwards of 15 other dots, thanks to something known as an R naught. Yep, R naught, a fancy term that tells you how contagious a disease is. The R naught of measles, around 15. The R naught of smallpox, 6. Both are very contagious, but measles remains rare, and no one gets smallpox anymore. Credit the rise of vaccinations, an effective shield against contagion. Maybe a few dots received one, maybe that one didn't. But see what it does to the spread? Now let's take the new coronavirus. Its R naught of 2 or 3 suggests it's not as harmful. But as of now, no one has protection. There is no vaccine. So you and your dot could infect 2 or 3. And those 2 or 3 could infect 4 or 5. And so on and so on. In the U.S., the number of cases is doubling every 3 days. A true case of exponential growth. But let's say you decide to social distance and only infect 1, not 2 or 3. Your neighbor doesn't go to work. Your coworker doesn't hit the park. A stranger stays home. Infections can still happen, but the odds of any one dot infecting 2 or 3 others decreases thanks to distance. The contagion slows. Exponential growth turns into linear growth, if not this. Until there is an effective treatment or a vaccine, physical distancing represents the best odds, say infectious disease experts, one by one, connecting the dots by doing nothing more than disconnecting them.
So as you can see, the video was created at the early onset of coronavirus a while ago, before there was immunization, and they were talking about what's the importance of social distancing. But the thing that I wanted you to get out of that is the spreadability. And again, this was before all the different variations came out of it. So it says, according to the video, the cases of COVID double every 3 days. So this was, I think, probably with the original strain. All right, so we're going to take that and we're going to take a look at what they mentioned in the video, the exponential growth of that. So it says, let's say that you attend 7 classes a day, and on average, each class has 30 students. If you went to school and got COVID, how long could it take to spread to everyone in your classes from just you if there wasn't immunization, social distancing, or anything that they talked about in the video? If you have 7 classes and each class has 30 students, we're talking about 210 students in all of your classes. So then it says complete the table below. If you notice, again, we talked about how that original strain doubled every 3 days. So day 0, let's say that you are infected. So the total number of infections is 1. After 3 days, the number of infections doubles, so there's going to be 2 new infections, but the total number infected is you plus the 2 new people, so there's 3 people infected total from that original strain. And then 3 more days pass, again the number of infections doubles, so this would be 4, and then the total number here, we're going to add 3 plus 4 and get 7 total infections. And again, it's doubling every 3 days, so we can just add 3 to the first column. So we'll have 9 days, 12 days, 15, 18, 21, 24, and 27. So this is every 3 days. The number of cases doubles, so let's just double this number, 8. If you double 8, you get 16, 32, 64, 128, 256, and 1,000. 20, nope, that's not right, 512. Okay, and then total number, so these are just the number of new infections every 3 days, the number of new infections. But then if we add it to the the people that were already infected, 7 plus 8 is 15, 15 plus 16 is 31, 31 plus 32 is 63, and we keep adding these together, and we'll start to look for patterns here. So it says, how long does it take until everyone in your classes gets COVID according to this table right here? And we said that there's a 210. So it would be between 18 and 21 days right here, where we're looking at 310, actually 310 people, so no, not in between those. We're looking in between here, 21 and 24 days. Again, the number we're looking for is 310 students getting infected. So between 21 to 24 days. So we're looking at between before a month is over. So between 3 weeks and a month, everyone is infected. And so, on the early onset of this disease, we didn't know very much, and that's why we say, social distancing is important. And now we talk about immunizations as well to stop the spread and social distancing of the disease. So that's a case of exponential growth where it seems to start out pretty slow, but then, if you're doubling something every 3 days, it starts to grow really quickly after a while. So with that in mind, we're going to take a look at the Cindy Lou Who problem, and this will be your assignment. It says, Cindy Lou wanted to get a part-time job to have extra money for the holidays. After reading the advertisement at the right, she applied. Her interview went well, and she was offered the job. She had to choose between 2 pay scales. So pay scale number 1, she would make $10 per minute. Pay scale number 2, on day 1, she would earn a penny. On day 2, it would double to 2 pennies. Day 3, it would double to 4 pennies, and so on. So before starting the problem, can you guess which pay scale Cindy Lou would choose? And she's working, she starts at, I think it's like the day after Thanksgiving, all the way up to the day before Christmas Eve. And again, which pay scale? $10 a minute, and she works, if you notice, from 6 to 9 right here, each of these days. So that's 180 minutes, so she's making $1,800 a day. Or you can earn a penny the first day, and it doubles every day thereafter. So pay scale 1 or pay scale 2, choose one. Which one do you think will make her more money in the long run? All right, number 2, complete the table to see which pay scale is better. Well, again, she's working 3 hours a day, so that's 180 minutes per day. So I'm just going to draw an arrow down. It's 180 minutes for all of these. And again, pay scale 1, it's $1,800 per day because it's 180 times $10 a minute. And then if we look at the earnings right here, we're just adding $1,800 a day. So 3,600 plus 1,800 is $5,400 she's made after working 3 days. Add another 1,800, we have 7,200 the next day, and so on. So you just keep adding $1,800 a day, and that's pay scale 1. Pay scale 2, we're taking our amount right here, and we're doubling it every day. So after the 3rd day, she's making 4 cents total. Well, 7 cents total because you add the earnings to date. But if we keep doubling this, on day 4, she'd earn 8 cents. On day 5, 16 cents. 32, 64, $1.28, $2.56, and that's just the amount per day. But to figure out the total earnings, we add. So like the first day plus the second day, we get 3 cents total. We add our earnings from the second day to the 3rd day, we get 7 cents. 7 cents plus 8 cents is 15 cents, and we just keep adding the amount that we had earned to our new amount that we earned that day to figure out the earnings to date, like the total amount if she saves everything. Okay, so for your assignment, I want you to complete this chart. So again, in this column of the 4th column over, you just add $1,800 a day. The 5th column over, you just double the amount. And then the 6th column, you take the amount from the day before and then add the new day to it to get the total earnings to date. So fill out this table, and then on the back side, there's some questions to answer. looks like 1, 2, 3, 4, 5, 6 questions to answer about what you noticed in your table, and then an extra credit problem. So do that before we look at day 5.